week 3 of the Calculus 10. Should be finding that these problems are slightly harder than the previous weeks. And if you're spending about half an hour each week just doing these problems, you should find that your skills with your differentiation and integration hopefully have improved. Now, as always, at this point you want to pause the video and have a go at these problems, and then unpause it, and then we'll start going through the solutions. So we start with y equals 1 over the square root of x cubed plus 2x squared. Now with this one, we want to use the chain rule here. What I'm going to do is firstly rewrite this as x cubed plus 2x squared in a bracket to the power of negative a half. Okay, if you square root something, that's the power of a half. Because we've got 1 over it, it's going to be a power of negative a half. And then I can just use the chain rule. As I've said in the previous videos, if you're a bit more confident with this, then you might just be able to differentiate it like that. But if there's any sort of doubt, I would always use the chain rule to do problems such as this. So I'll just explain here what I'm doing. So I'm making a substitution of what's in the bracket. I'm going to call that u. And that just means my y now is just u to the power minus a half. Do your dy by du. So multiply by the power, take 1 off the power. And then differentiate your substitution. So find du by dx. And then remember we times dy by du and du by dx together. But what I'm going to do is I'm going to replace the u back with the x cubed plus 2x squared. And that will be my answer for the first one. Okay, it looks quite nasty, but that's correct. Not too much more simplifying we could do there. The power minus 3 of 2, there are different ways that you could write that, but unless specified, you can just leave it how you want to. Question 2 then. We've got y equals 8 to the power of x plus e to the power of root x plus natural log of tan x. Now, really with this problem, it's just a way of kind of putting 3 problems into one here. Just kind of going through these term by term. So I'm going to start off with, I'm going to do these separately. I'm just going to keep using y each time, just so it doesn't get confusing if I use a, b, and c for each part of it. So I'm going to start off by differentiating the 8 to the power of x. When you differentiate a to the power of x, you write down a to the power of x and you multiply it by the natural log of a. Okay, so in this case the a is an 8. So we write 8 to the power of x and then we multiply it by natural log of that base, so natural log of 8. If you want to see more about how we differentiate functions in the form a to the power of x, in the previous week I go into the actual proof of that. So if you want to see the proof of that, just go back and watch the previous week's video. So then we have y equals e to the power of root x. Now I'm going to start taking a few shortcuts here. Again, if you go back to the previous videos, I've got examples of differentiating e to the power of different functions, and I'll go through it with the proof of the chain rule. Here though, I'm just going to kind of find some quick way of doing it. It's going to help us with the integration a little bit later as well, spotting this quick way. So with the exponentials, as e to the power of root x. I just write e to the power of x, and I multiply it by the derivative of the power. So if I differentiate the square root of x, that's x to the power of a half. So multiply by the power, take one off the power. So that's what I need to be multiplying this e to the root x by. Okay, so that's the second term differentiated. Now for the last one, I've got y equals the natural log of tan x. Yet again, if you want to see the previous videos, I've got examples of differentiating natural log of some function of x using the chain rule. Here I'm just going to take a shortcut again. What we find is when we differentiate natural log of some function of x, you put that function on the bottom of the fraction, and then you put its derivative on top, which is going to be sec squared, and that's how we differentiate natural logs as a function of x. Yeah, again, if you're in doubt with that, check the chain rule, and you should hopefully get what I've written there. So for the answer to the whole problem, I'm just going to write it all out here. So differentiate the first term, we get that natural log of 8 to the power of x. Differentiate that second term, we've got this half, x to the minus a half, e to the root x, and then we've got our final term differentiated at the end. Yeah, again, I've not specified any particular way that you should leave this, so leaving it like this should just be fine. Right then, 3 then, we've got cos x sine y equals xy. So the goal with all 5 of these differentiation problems is to get dy by dx. So what I'm going to do is I'm going to differentiate both sides with respect to x. So I'm going to start here on this left hand side. Now I've got a function of x times a function of y. So I've got a function times a function. I can't really simplify this, so what I need to use is the product rule. So the product rule, we take the first function, so if I have a u equals cos x and I have v equals sine y, I'm going to find my du by dx, which is going to be minus sine x, and I'm also going to find dv by dy here. Oh, sorry, first time I'm going to find dv by dx. So we're going to find dv by dx. So I differentiate sine y with respect to y, which gives me dy cos y. Okay, so differentiate sine y with respect to y to get cos y. However, though, I'm differentiating with respect to x, so I need to multiply this by dy by dx. This is an implicit problem, so if this doesn't seem, we have done examples in the previous videos, but if you need a little bit more practice with this, go back and do some implicit differentiation. And then I can just multiply the second function times the first one differentiated, so that would be minus sine x sine y. Then add the product of the first function multiplied by the second function differentiated. Then we need to differentiate this right hand side as well. I'm going to do this without showing all the u and the v here, but yeah, again, write it out with all the substitutions if you need to. If I differentiate the first function, I get 1, and then I'll times it by the second one not differentiated, so it gives me y. And then if I multiply the first function times the, if I differentiate the first function and multiply it by the second one, not differentiated, then I'm going to get x times dy by dx. So what happened there was I've got x, my first function. If you multiply it by the second function differentiated, we differentiate y, you get 1 if you differentiate with respect to y. But because we want to differentiate with respect to x, we need to multiply by dy by dx. Okay, so it's x times 1 times dy by dx. Then what you would need to do is group your dy by dx's together. Group all your non-dy by dx's on the other side, and then just do the division there at the end, and then that's our result. So the next problem is y equals sec over x squared. So differentiate this, we want to use the quotient rule now. So I'm going to call what's on the top of my fraction sec. I'm going to call what's on the bottom of my fraction x squared. And for the process of the quotient rule, so I'm using the quotient rule because it's a function divided by a function. So differentiate sec. This you can find in your formula book. It's sec times tan. And x squared, differentiate that, you get 2x. Okay, so we're going to need this as part of the process. So to do this with the quotient rule, on the bottom of the fraction goes v squared. So if you've got x squared and you square that, you're going to get x to the power of 4. With the quotient rule, unlike the product rule, the order definitely does matter. You need to do this v times du by dx first. Now you do get the formula for the quotient rule in the formula book. You don't get the formula for the product rule. So do make sure you just double check with the formula book when you do these problems. So multiply v times du by dx. And then multiply u by dv by dx. And if you're asked to simplify further, you can do, but really this is it in terms of what you need to do here. The final problem for the differentiation then is going to be where we've got some parametric equations. And just another reminder, especially because in the advanced material, the question with, differentiating parametrically is specifically mentioned. So that's why I want to keep putting in ones like this. So as I mentioned with last week's example with parametric, you don't need to find the Cartesian equation here. So you don't need to get this as y some function of x and then just find dy by dx. What we can do is find dx by dt and find dy by dt. So finding dx by dt, just be really careful. We need to use the product rule here because this is t times natural log of t, so a function of t times a function of t. So use the product rule. Differentiate t, you get 1, multiply that by the second function. And then differentiate natural log of t, you get 1 over t. So we do t times 1 over t, and we should spot that the t's there are going to cancel, giving us just a 1 there. So you've got, when you differentiate, that's going to be natural log of t plus 1. dy by dt, this should be straightforward enough to differentiate. Just multiply by the power, take 1 off the power, and then your 4t would just become a 4. So to find dy by dx, we do dy by dt divided by dx by dt, because your dt's are going to cancel. So your dy by dt goes on top, your dx by dt goes on the bottom, and that is it. Okay, remember, with a lot of these questions, when you get to the exam, they're going to ask you to do other things with them. It's not going to just be just differentiate this or just integrate that. So obviously do look at problems with this, but the idea behind these videos are just so you've got the base skills there, so you can do the differentiation and the integration in the first place, and then you're fully prepared to do those extra questions. Right, let's get on to the integration then. So integrating first, 3x squared times e to the power of x cubed. This looks really horrible when we first see it, but it's not as bad as you might first think. We don't want to use parts here. We don't want to use substitution if we can avoid it. I mean, you can use substitution if you're not sure. A substitution of u equals x cubed should do the trick here. However, what I can do is try and just do this by recognition, which means I should be recognising that I've got an x cubed here, and I've got the derivative of x cubed here. So what I should try is, sorry, it should be equaling try. So if I try y equals e to the power of x cubed, but when I differentiate that, so as we talked about previously, we differentiate exponentials, we multiply by the derivative of the power. So the derivative of the power is 3x squared, and we can see that when we differentiate e to the power of x cubed, we get 3x squared e to the power of x cubed. That must simply just mean that's the answer to the problem. Obviously, we need to put a plus c there as well. So if you have, if you integrate something, if you want to check it, then you can just differentiate it and you should get what you started. And we've proven on the right hand side there that if we differentiate e to the power of x cubed, we do get 3x squared times e to the power of x cubed. So always be on the lookout for, can you see derivatives of functions within the question? Because then you can save yourself a bit of time if you can spot it via recognition. If not, you could use substitution here, as I mentioned. So if you let u equal x cubed, you'll be successful in being able to do it by substitution. But as we know with substitution, it is quite a long process some of the time. So if you can spot it there and then excellent. The next one then we're going to look at is we're going to integrate sine 2x cos 2x. Now, can't do this one by recognition. Whilst when we do differentiate cos, we get sine and vice versa. We won't be able to do this one by recognition. So what we're going to do instead is use trig identities. We don't want to go down the approach of integration by parts. Similar with the last one, just be too time consuming to do so. What we're going to look at then is recall that sine 2 theta equals 2 sine theta cos theta. So really important to know your double angle formulae. They'll come into play quite a lot here. Not just in the trig, but with your calculus as well. So this is almost similar to what I've got to integrate, because I'm integrating sine 2x cos 2x. So it's not quite in that form of 2 sine theta cos theta, but what we could say is, well, theta is, instead of just being an x, it's 2x. So what we've got is sine 2x cos 2x. So we'd have a sine 4x. Now, also another difference is we have 2 sine cos x, but what we're actually trying to integrate doesn't have the 2. So if it's just sine 2x cos 2x, it's going to be a half sine 4x. Okay. If it was just sine 4x, it would be 2 sine 2x cos 2x, but we don't have a 2 there, so it's just half sine 4x. So that is what we are integrating. So integrate sine 4x, the sine, that's become a negative cos. Remember, it's when you go from sine and you're integrating it, you go to the negative cos. And then we're just going to divide by the coefficient of x, which is 4. So a half times a quarter, a half divided by 4, is just going to be an 1/8 cos 4x plus c. Now our next example, we could actually do it via recognition, and that's probably the way I would go about it, but it might be a bit of a harder one to spot. So I'm going to use this as another opportunity to do some integration by substitution here. So the problem is, oh, and also what's different about this one as well, we've also got limits. I don't think we've done any in the previous video where I've had a definite integral, where I've had limits here. So this should be a nice little reminder of what we do here, just in case you've forgotten. So the substitution we're going to use is u equals sec. Now, as I normally say with these integration by substitution questions, differentiate your substitution first. So I'm going to differentiate sec, which in the formula book you can find. We did it in a previous problem in this video. When you differentiate sec, you get sec tan. So, and before I go and sub everything in, because I've got the limits, what I also want to do is change them. So I'm not working with these x limits, I'm actually working with these u limits. So I've got pi over 4 and pi over 3 to sub in. So when x is pi over 4, when you sub it into your substitution, you end up getting 2 over root 2. Okay, remember, you don't have sec on your calculator, but what you can do is find cos of pi over 4, which is root 2 over 2, and then just do 1 over that. Okay, so remember, with those reciprocal trig functions, just find sine, cos, or tan, and then do 1 over it. And then when x is pi over 3, so cos of pi over 3 would be a half, so sec of pi over 3 is going to be the reciprocal of that, it's just going to be 2. So now we have our limits of 2 on the top and 2 over root 2 on the bottom. Now in terms of cancelling this down, what I should notice is my derivative here of the substitution, du by dx, is sec tan. And in the question, we should see that we've got a sec tan there. We then would still have another sec cubed, but that's taken care of by our substitution. So I'm just going to separate this all off first, so we can see nice and clear where everything's coming from. So I've got just separating the sec to the 4 times the tan, and then I'm going to replace the dx with du over sec tan. Okay, all I've done there is just rearrange the du by dx equals sec tan to make dx the subject, because remember, with my substitution, I want to end up with all u's here. So I'm just going to do that. And the reason why this works is because if you replace the dx with du over sec tan, the sec tans are going to cancel, and sec cubed can just get replaced with u cubed. Okay, sec is u, so if you're cubing it, you're going to have u cubed. Integrate u cubed, which should be nice and simple. Add 1 to the power, divide by the new power. And then just plug in your limits of 2 and 2 over root 2. And we should find that we just get 3. Okay, 2 more to go and then we're done. So this next one, we're going to integrate 3x plus 10 over 2x plus 3x minus 4. Now with this one, the method we want to use here is we want to use partial fractions. I do believe in the advanced material it's the differentiation question that has partial fractions with it. So I think there's going to be a question where you're doing a differential equation and you're going to have to end up integrating something where you need to use partial fractions. Whether they'll give you that hint or not, well, we'll have to find out next month. So I'm going to split this up. So remember, partial fractions, you want to have one of your terms, one of the factors with one constant on top, and the other factor with a different constant on top. So if they don't set it out for you in the exam, make sure that you know how to do so. And then we're just going to multiply through by 2x plus 3x minus 4. So for the first fraction on the right, the 2x plus 3's cancel, and we get x minus 4 here. For the second fraction, the x minus 4's cancel, and I just end up with the following. Then I just make some substitutions. So firstly, I'll let x be 4, because what's going to happen is the first bracket on the right is just going to go to 0, which just means I can find what b is. So I'm going to do that. I get 22 on the left hand side, I get 11b on the right hand side, which means I get b is 2. Then I'm going to let x equal minus 3 over 2, because that's going to make the second bracket on the right equal 0. And I end up getting 11 over 2 on the right, on the left, and minus 11 over 2a on the right. That means that a is minus 1. What I can do now is I can just put the b on top of the x minus 4. I can put the a on top of the 2x minus 3. So this gives me 2 over x minus 4. Just going to reverse the order at which I did it, so I'm not leading with the negative. Not that it matters, but just what I'm going to do. So this is what we're going to integrate here. So when you've got a linear function of x on the bottom, you've got a constant on top, you want to be thinking natural logs, okay? Because remember, with natural logs, like we said earlier in this video, when you differentiate them, you put the function on the bottom, you put its derivative on the top. So if you differentiate a linear function of x, you get a constant. So differentiate the first one, that's going to be 2 natural log of the modulus of x minus 4, because when you differentiate x minus 4, you get 1, okay, but then we just multiply it by 2. Be a bit more careful with the second term. When you differentiate 2x plus 3, you get a 2. Now, there's not a 2 on top there, there's only a 1, so we're going to need to multiply that by a half to compensate for that. It's a similar thing we've seen with other problems where just make sure you multiply by 1 over that coefficient of x when you've got integrating something where there's a linear function of x within something else. And don't forget the plus c. As always, you can always check it by differentiating this one back. Now the final problem we're going to look at is going to involve differential equations. So the problem is you've got dx over d theta equals cos squared x cot theta. Okay, and we were asked to find the general solution. Okay, questions could go a bit further and ask you to find particular solutions or find the value when theta or x is this, but I'm just going to keep it relatively simple. The first differential equation problem we've got here, and then maybe next video we'll look at some slightly harder ones. So the first thing we want to do is separate the variables. That means anything involving an x or a dx is on one side, anything involving a theta or a d theta is the other. Any constants you have, think of them as neutral, doesn't matter what side they're on. So we'll divide both sides by cos squared, and I'm going to times both sides by d theta, because now I have all the x's and dx's on the left, I have all the thetas and d thetas on the right. So what I'm going to do then is I'm also going to stick an integration sign on both sides. I'm also going to rewrite 1 over cos squared as sec squared. And then you just integrate both sides as you go along. So integrate sec squared, we get tan x, because remember when you differentiate tan, you get sec squared. That result is in the form of the book though, if you weren't sure. Integrate cot. This is also in the formula book, and you get natural log of sine theta, and then we just put a plus c there. Now some questions might ask you to leave it in the form of y equals this, or y squared, or tan x equals. Again, we haven't got that information here, so we're just going to leave it like that as our general solution. And to be fair, there's not really a huge amount you could do anyway in terms of rearranging. Other questions will then go on to give you some boundary conditions to be able to find what the plus c is, so you can get your particular solution. But for now, I'm just going to leave it as the general solution. As always, just make sure you do put that plus c. If there are any questions with any of these questions, or you want to just suggest things that you want to do in future videos, just leave a comment or come talk to me in college, or just leave something on Teams, and see you for week 4.